Okay. Thank you. All right, so today we're going to switch directions and consider the Bernstein problem, but for the minimal surface equation instead. And so everything we did yesterday for the Monge-Ampere equation was pretty much based on the maximum principle. Today will be a more variational approach to the problems. Minimal graphs. So overall, over the next 2 days, take everything that Professor Urbano talked about yesterday and just stretch it out over 2 lectures. We'll just dive a little bit deeper into the story. Okay, so let me just start with a few preliminaries related to stability. Maybe I'll start. So if we have some, let's say, smooth-oriented hypersurface in Rn plus 1. Hypersurface that has some normal nu. Then one thing which will be useful for us is to understand how the mean curvature of sigma changes under a small normal deformation. So we've already seen something related to this in Professor Urbano's lectures, but just so here's what we want to do. So we'll take sigma, we'll make a small perturbation of it. We'll call this sigma tilde in the picture. And the way that we do this is we pick some smooth compactly supported function on the hypersurface sigma, and we just move by epsilon times that function in the normal direction. So we have a domain omega and sigma, a function phi, smooth compactly supported omega. And at each point, x and sigma, we want to move in the normal direction, a little distance epsilon times phi. So let's tilde, I'll give this a better name, sigma epsilon. Epsilon be sigma plus. So is this notation clear to you? We're just moving epsilon times phi in the normal direction. And the first thing is that the mean curvature of the new surface sigma epsilon. We don't need this to be minimal. I'm not talking about minimal yet. For any hypersurface, the new mean curvature is going to be the old mean curvature. They add the point x plus epsilon phi nu. The mean curvature of the old surface at x plus epsilon times the Jacobi operator applied to the function phi. So this is the Jacobi operator. What the Jacobi operator is capturing is exactly how the mean curvature changes under small deformations. And from this, we immediately see, in fact, an important fact that Professor Urbano mentioned, which is that the components of the unit normal in Euclidean space solve the Jacobi equation because they generate translations of the surface. They don't change the mean curvature. So P is equal to nu dot any coordinate direction ek. Then this generates translations. In other words, if I choose this choice of phi, and I do this deformation, it just translates by epsilon to leading order in some direction. And this tells us that. Okay, so that's one thing. Now we'll restrict ourselves to studying minimal hypersurfaces. We'll expand the area second order. which is equal to 0, then the area of the perturbed surface, epsilon over the area of sigma, plus, so there's no term involving epsilon because the mean curvature vanishes. It's a critical pointed area, so we have epsilon squared over 2 times the integral over sigma of minus phi times Jacobi operator applied to phi. And we say that this domain omega is stable if this quantity here is always non-negative. So small perturbations will always increase the area. It's bigger than or less than 0. So minus sign. Okay, so we've seen this in previous lectures. And let me just remark that this is equivalent to saying something about the eigenvalues of the operator L on the domain. Namely, if you could try to maximize this quantity, subject to the constraint that the L2 norm of phi is 1, and you'll simply get the maximal Dirichlet eigenvalue of the operator. This is the same thing as the maximal eigenvalue. Well, omega is less than 0. All right. So I just want to say a few small observations related to this about criteria for stability. So one thing we can say right away is the following. So, first of all, if we want to prove that a minimal surface is unstable, all we need to do is to find a positive subsolution of the Jacobi operator on the domain. So if there exists phi, put W1 such that it's a subsolution, so L phi is bigger than or equal to 0. Say phi is bigger than 0 in omega, so it's positive, it's a subsolution of the equation, and if this is a strict inequality somewhere, then we get instability. And this is supposed to be obvious. You just plug phi into that expression, and if phi is positive and L phi is positive, that's just not going to hold. That's it. And so like a very natural approach to, for example, showing that a minimal cone, which is not flat, is unstable, is to try to find one of these guys. The second thing, which Professor Urbano also mentioned, is that if you manage to find a positive super solution of the Jacobi operator, then you have stability. It's a criterion for stability. So if there exists, say, P bigger than 0 on sigma, such that Jacobi operator applied to V is less than or equal to 0, then we have omega is stable. And a short explanation of this would be the following. If omega were stable, that would mean that, if omega were unstable, if it were unstable, that would mean that the principal eigenfunction has a positive eigenvalue. So if you look at omega, you look at the principal eigenfunction, which is positive. So if function. It vanishes on the boundary, it's positive, and it's going to be we'll call it W. All of W is going to be positive inside the domain because W is positive there. It's not a function. And if you look at this function B, which is positive, and you simply take multiples of V, then an appropriate multiple is going to touch the function W from above somewhere. And if V lies above W and they touch at some point, then we just contradict the equation. It's maximum principle. So here, this contact point can contradict. I would say this is a maximum principle explanation of what Professor Urbano explained a couple minutes ago. Okay, so in other words, to prove that a minimal surface is stable, look for a positive supersolution of the G. Any questions about that? So now we'll restrict ourselves to minimal graphs. So now, from here on out, sigma will be an entire minimal graph. Draw like this. Graph over psychology. Let me just remind you of something. So first of all, if you look at the unit normal, the fact that this is a graph means that the vertical component is positive. So that means that the unit normal is always pointing upwards. So this distance here is this guy here is a solution of the Jacobi operator, which is positive, so that's stability. Just reminding you of this fact. Just reminding you of the fact that graphs are stable. But we could say even more. So an important fact is that a minimal graph is, in fact, area minimizing. So in fact, sigma intersect any extrinsic ball, ER, this is in our next one, is area minimizing. Roll. There are a couple of proofs of this fact, but one of them that I like is known as the calibration technique. So it's just like a two-line proof. So let's draw sigma once more. It's here. And we're going to show that if we make any perturbation of the surface, then we get something with larger area. Let's look at some competitor. Doesn't have to be graphical. This, your sigma tilde. What we'll do is we'll take the unit normal vector field on sigma, third color, nu, and if we just extend it to be constant in the vertical directions, it satisfies what we call as the calibration property. So extend nu to be constant. So as a function of the variable x It's down here. It was just the expression I was getting to. You can just think of, this is a variable x down here. This one up here. It was a vector field on the whole ambient space that just only depends on this variable. And what the minimal surface equation tells you is that the divergence of this vector field vanishes. Surface equation. In fact, just exactly the same thing as divergence. R plus 1 of this vector field is 0. So divergence of this first part of 0 is the minimal surface equation. And this last term doesn't depend on the last variable, so it doesn't contribute. And so we're just going to use the divergence theorem. So if nu tilde is the unit normal to sigma tilde, and we call the region in between these two guys, I'll just give this region a name. And 0 will be the integral. Nu. We have, when we integrate by parts, two boundary contributions. The first part is when we integrate nu against, so I don't know what it is, nu over here is this. Integrate against the sigma tilde, we'll get nu dot nu tilde. That's one of the boundary terms. And the other boundary term is going to be an integral over sigma of nu dot itself, which is just area of sigma. And now we're done already. Why? Because this is the area of sigma. Because these are unit vector fields, this is certainly bounded above by the area of sigma. So we just move this over and we have the inequality. Okay, so what is this good for? In the context of the Bernstein problem, one thing this is extremely useful for is to get area bounds for the graph sigma. So a consequence of this, the following is if, for example, say 0 is an hypersurface sigma, then the area of sigma intersect all of radius r over 0 is bounded above by the Euclidean growth of the ball in Rn. So it's constant depending on dimension. This is supposed to be kind of obvious because if you have this ball radius r, centered at a point on sigma, then you can generate a competitor for area by following sigma outside of the ball, and then just replacing it by the boundary of the ball where sigma is inside. So if you follow this, you can only increase the area of sigma, but we know that the area of the boundary of the ball of radius r is this guy right here. So just use And from here, we'll actually segue into the next important thing, which is that this quantity, looking at the area inside the ball of radius r, of course, is a natural quantity to look at because we're looking at surface area when we talk about minimal surfaces. Surface area. And if you look at a scale invariant version of this quantity, it happens to satisfy an extremely special property called the monotonicity formula. Namely, if we're in the same situation, say zeros and sigma, and if we look at the quantity, the area of sigma inside the ball of radius r, so this area here, we divide by r to the n. We know we'll get some number that's bounded independent of r by the area bound. But the point is that this quantity here, called v of r, is non-decreasing in r. So it goes down. And moreover, if it happens to be constant, then sigma has to be a cone. Namely, if you take dilations of sigma, then you just get sigma back. So this is the trick that Fleming and Georgia used to reduce the current time problem in studying cones. Let's just explain briefly why this should be true. All the proofs I'm doing today are in quotations. They're not rigorous, they're just ideas. So look at sigma, it might look something like this. What we want to do is just to compare sigma to a cone, which has the same link on the sphere. So you look at sigma intersect, so there's the ball radius here. You look at sigma intersect the boundary of the ball, and you just take the cone over that n minus one-dimensional surface. This is a cone, K, which agrees sigma on the boundary of the ball. And for the cone K, this quantity here is obviously constant just by its dilation invariance. So how the area of K is growing is exactly like so if we look at how this quantity is changing for sigma, let me just write down what it's going to be. It's going to be how fast the area is changing. R minus n times the area. And plus 1. Here, all I've done is just differentiate this quantity. So we just use the quotient rule. And I'm just going to do something very naive. So first of all, let's look at how fast this quantity is changing. So if we look at how fast the area of sigma is changing, as we increase the radius a little bit, it's going to be increasing faster than that of the cone K. The reason is that sigma intersects the boundary transversely in general. So this little area right here is always going to be bigger than the area of K, which intersects orthogonally. So I'm not using anything about minimality. This is just some Euclidean geometry. It says that this quantity here is going to be bigger than the corresponding quantity for K. And for the second term, notice that the area of K in the molar radius R has to be smaller than that of sigma because sigma is a minimizer of the area. This is always going to be smaller than or equal to here we just use that sigma as minimizing. Okay, so it's obvious that this whole quantity here is larger than the same thing if we just replace sigma with K. Turn my term. This is going to be bigger than the same. K instead of sigma. But as we said, the same quantity with K instead of sigma should be 0. Because that's the quantity associated with the cone K is not changing. And if you just carefully study when equality happens, it's only going to be happening if this transversal intersection is in fact exactly orthogonal. So it has to be. And just study the whole cases. So actually, this is a very common theme in variational problems. You're handed an energy, and you have a critical point of that energy. Look at some quantity which involves the energy in the scaling invariant. And then compare that quantity with something which is appropriately homogeneous with the same boundary values. I think it's important to see this one because this is like the simplest monotonicity one. Okay. So now I'm just going to combine the two things that we just talked about. So the fact that sigma is minimizing with the area bounds of sigma, plus monotonicity formula, and some theory which I'm not going to talk about, allow us to say something. Area bounds. Formula. They tell us the following. That if you take your entire minimal graph sigma and you start zooming out, so you start sort of dilating sigma by smaller and smaller constants, then you should eventually end up at a cone, which is also area minimized. It exists members Rk going to infinity, such that sigma divided by Rk converge to infinity to an area minimizing. The area bounds are basically used in order to get convergence of some subsequence to an area minimizing object. And the monotonicity formula will tell you that the limit is a cone. You can think that as you blow down more and more and more, this quantity here is kind of approaching its maximal possible value. Like the limit is the R goes to infinity if this thing exists by its monotonicity. And after you blow down, you get a cone for which the corresponding quantity is finite infinity. Okay. And the last thing I want to say before going on to something more specific is that if you can prove that all the area minimizing cones in Rn plus 1 are flat, or hyperplanes, normal area minimizing. Hyperplanes. Then I claim that sigma has to have been a hyperplane to begin with. So what's the reason? So the reason is the following. We took sigma, we zoomed out another again and again and again until we ended up with a cone, area minimizing cone. We said, okay, well, this cone has to be flat for some reason that we haven't talked about yet. And that means that this value phi for that limiting cone is that of just the flat plane. So phi of the blowdown cone. By blowdown cone, I just mean this guy right here. It's the same thing as phi of plus infinity for sigma. But we know that this is the same thing as the plane. We know that the blowdown cone was a plane. But sigma was some smooth entire minimal graph. So that means that near zero, this quantity for sigma should also be that of a plane, because sigma is basically flat at small scales. But for sigma, phi of 0 is also phi of hyperplane. The reason is that it's a smooth minimal graph. So if you take a very small ball centered on sigma, and you look at its area, it's more or less the same as the area of the tangent plane. Okay, but now we're done by the monotonicity formula, right? Because that means that phi of plus infinity for sigma is the same thing as phi at 0. So that means that sigma was a cone to begin with. Phi sigma is constant. Sigma was a cone. And because we know that the blowdown cone was a hyperplane, sigma was in fact a hyperplane. So I think that's sort of obvious. All right. So all of this is the basic ideas in the theory of reducing the Bernstein problem to showing that area minimizing cones are hyperplanes. So now the goal from here show that area minimizing cones are flat in low dimensions. In fact, what we're going to show is that stable flat So in other words, what we want to do is the following. If we have a minimal cone in small dimension, which is not a hyperplane, we want to show it's unstable, right? And recall from the very beginning, this is the same thing as finding a positive solution of the Jacobi equation. So we need to find natural quantities and compute the Jacobi operator applied to them and try to show that they're positive. And this is exactly what Simons did. He showed that if you look at the curvature of the minimal surface and you apply the Jacobi operator to it, then you get a favorable sign. This is the key thing is called Simons identity. So it says the following. The identity is the following. That sigma is minimal. And we'll let the second fundamental form of sigma squared, so the sum of principal curvature squared, I'll call it c squared. Just to agree with notation from where I learned this theory, book of Enrico Giusti. Then what we know is that the Jacobi operator applied to c squared. So actually, the basic thing is the 1/2 plus of c squared plus c fourth. That was the same thing as the gradient of second. Or another way of writing this is that c times the Jacobi operator applied to c. I just expand this. All right, so if we want this to be positive, I need to get some sort of bounds for this quantity right here. Show it's non-negative. And that's the Simons inequality. To talk about that, let me just say one thing. So in the notes that I'm writing, actually, I prove this identity. And I find it easiest to establish in the situation that you write sigma locally as a graph of some function, and you calculate what this is at a point where the gradient vanishes. I'm just going to write what this is. Sigma is the graph function W. W is 0. So that's 0. Another way of writing this right here is that at 0 we have C. So in terms of the function W, basically you just write the second fundamental form in terms of this function W. If you perform the calculations at the point where the gradient vanishes, life gets a lot simpler. A lot of things cancel out. That allows deriving this to be a little less annoying. What you get is the sum for I, j, k, third derivatives, w, I, j, k, squared. Minus, and the gradient of c squared looks like the following. So if we assume that the Hessian of w is diagonal at 0, we get the following. It's going to be this quantity minus 7k. So over I. Okay, so I did this calculation for you in the notes. I'm not going to do it here, but that's just this first quantity in terms of W. It's right here. The second quantity in terms of W is exactly this right here. And to show that this is non-negative, all you need to do is just to do some sort of Cauchy-Schwarz. You apply Cauchy-Schwarz right here. Oops. This is bigger than or equal to sum of there. Minus sum. So I just apply Cauchy-Schwarz to this guy, cancel those two, you get this. And now we just do something sort of combinatorial. So first of all, this is certainly going to take care of all of those terms. We'll get something non-negative, but I want to be more precise. So whenever I and j agree, we get sort of we lose all the things on the diagonal here. And over here, we'll also lose all these quantities when I is not equal to j, but only one copy of them. If we look at this sum, and we look at all possibilities of where two are the same and one is different from the rest, there are three ways of doing that. You can either make the first one different, the second one different, or the last one different. And we're only losing one copy of that. So just some combinatorics says this is bigger than 2, sum over I not equal to j. Or so we're getting closer to the inequality that's going to be most useful for us. So all these calculations hold just for a general minimal hypersurface. Now I want to restrict to the case that sigma is a cone, because this is the thing that's interesting for us. If sigma is a cone, then this term can be written in a particularly appealing way. Let me just draw a picture to derive that. So sigma at the point 0, I want to write it locally as the graph. This will be the vertex of the cone. This I'll write as a distance r. And what sigma looks like is something like the following. I'll say this is the x-end of lower end. I'm writing sigma locally as the graph. And what sigma is locally as the graph is a function which is homogeneous of degree 1 with the vertex as its origin. The point is this, so this is the x-end direction, and I want to calculate what this guy is at that point. What we have is the following. So first of all, maybe I'll write one more inequality. At 0, okay. At this point right here, if you choose j is equal to n, you differentiate the rest, then you'll get something interesting. W-I-I-N is what? Okay, so the point is this, is that W is homogeneous of degree 1, so its second derivative is a homogeneous of degree -1. Differentiate twice, homogeneity drops by 2. And if you differentiate that in the radial direction, that means that you're just getting the same thing, but minus sign divided by distance. So just by homogeneity, this is the same thing as minus Wi of 0 divided by that distance there. By homogeneity. So I'm not doing anything fancy. I'm just using the fact that the cone is a one homogeneous structure to get this expression. So for the cone, if I want to write this thing right here, it's for sure bigger than or equal to 2, the sum over I less than n. And using this identity here, this is in fact the same thing as twice. Then we have this squared over r squared. So in fact, we just get c squared divided by r squared. This just becomes the fact that some of So if you write a surface as a graph where the gradient vanishes, then the second fundamental form is just vanish. All right, so we're just going to put all this together and circle the big inequality, which is that so we founded this from below, that guy right there. We have L of C is going to be bigger than or equal to 2c over r squared. Oh. All I've done is we've estimated this from below by 2c squared over r squared, and now I'm just dividing this. So that's the Simon's inequality. Okay, so this is very good. It says that okay, if we have a minimal cone, and we apply the Jacobi operator just to the curvature squared, then we see we get something positive on the right-hand side that could be useful to us. The problem is that C is not compactly supported on some domain in the code. So we can't immediately use this to get some sort of contradiction of stability. So we need to use a cutoff. Now let's sigma is the cone. So just be vertex x equal. And let's apply the Jacobi operator to C, but we multiply by a cutoff function which depends only on radius. By some function which depends on radius. But psi be a function of x. So psi is just a radial function of. And let's just apply the Jacobi operator to psi times c. See what we get. So we'd like to just do a cutoff type argument. What we get is the following. First of all, when the Jacobi operator only hits C, we have an inequality. C over squared. Psi. Plus, we'll get one extra term, which is twice the dot products of the gradients. So 2 grad C. I'm going to write it in a simpler way. Because psi is a radial function, this is just the derivative of psi times the radial unit vector. And C is homogeneous of degree -1. So this is just psi prime times the radial derivative of C, which is minus C over R. Minus 2 psi prime R. Here. And the last term is just C times the Laplacian of psi, which I'm just going to write the usual formula for the Laplace in polar coordinates. So it's going to be C times 2 radial derivatives plus n minus 1. So R is probably confusing you. This term here is the plus. Here I'm implicitly using that this is a minimal cone. I write this one. Minimal. So the magic is almost about to happen. All right, L of psi times C is, I'm just going to write this as follows. C of prime from here. We have n minus 1 minus another 2 copies. Psi prime over R. And then we have 2 times psi over R squared. I'm going to actually split that into 2 pieces. You'll see in a second why I did this split. Bigger than or equal to. Okay, so with this formula in hand, what I claim is the following. All we need to do is to find a solution of this ODE with right-hand side 0, which is oscillating. This is what we need to do. So we need a solution to this ODE 0 that oscillates. This is R. What I mean is that it does something like this, where I have 2 values, A and B. The solution of this with right-hand side 0 should vanish. That's what I want. But if we do that, we're done. The reason is that this term would vanish. And in this annulus on the cone from A to B, so on the cone, intersect this annulus, all radius B minus all radius A. We have that L of psi times C will be bigger than or equal to psi over R squared. And this thing would be positive, but vanishing on the boundary. Boundary, I'll call this omega. Right, just because it's just you're just taking this angular region on the cone, it's vanishing on the first radius. So if we did this, we would be done, because if the cone had non-zero curvature, this is exactly the kind of function that would say that the cone is unstable. Unstable. If C is not 0. Okay, perfect. So in the last minute, we can use the condition that this has an oscillating solution to find exactly the dimensions where this is going to work. So we need, so look at the ODE, T double prime plus well, oscillating solutions. This is just equivalent to saying that like the nearby minimal surfaces of sigma always cross sigma. They don't go out of one side. Okay, well the solutions to this are easy to write down. You just take radius to a power. Just by the homogeneities. So R to the lambda are solutions for appropriate lambda. And You just plug this in, this is the condition you need to satisfy. In order to have an oscillating solution, we just need that this lambda has a complex component. Just need lambda not to be real. And the condition for that is exactly that the discriminant of this quadratic polynomial is safe. So I'll just rewrite it. This is n squared plus 0. We just need this squared to be smaller than 4 times 2 minus epsilon. Okay, and this is going to give us the basic, almost the optimal equation. So if you square everything over, we take the square root of everything over, we just need n less than 4 plus 2 minus epsilon. You can say, okay, if you take epsilon as small as you can't get up to n is equal to 7, but you can get all the way up to 6. 0. So in fact, this is the optimal dimension for stable implies flat for cones. So 6-dimensional cones in R7 which are stable or flat. And all of this tells you that if you look at minimal graphs in which are 6-dimensional in R7, then they also have to be flat. Doing the blowdown, classifying cones, and so on. Of course, there's this issue, you can actually go 1 dimension higher. That's related to the question that Stephen asked yesterday at the end. And I won't talk too much about that, but basically what you can show is that if you look at the blowdown cone of a minimal graph, then you can arrange that, see, if the minimal graph were not flat, you could prove the existence of a cylindrical minimal cone in Rn plus 1. So a cone of the form something in Rn cross R. So that gives you 1 extra dimension for graphs. But I'm out of time now, so I'll stop there. Yeah. Yes, I know. Well, okay. I'm assuming that the cone is smooth outside of the origin, so ignore this issue. But of course, if you have any smooth hypersurface, then you can locally write it as the graph over the tangent plane. If you have any smooth hypersurface, then you can write it as a graph over its tangent plane locally. That's what I was.
Really? No, so it's the same complicated.
Beautiful.